Sound by Ella Nielsen. Sound is a classic example of a longitudinal wave. Sound waves have very interesting qualities. Instead of peaks and troughs of transverse waves, sound waves are composed of condensations and rarefactions of the medium through which they travel. Particles in a sound wave move in simple harmonic motions along the direction that the wave travels. Longitudinal waves are waves in which the motion of the individual particles of the medium is in a direction that is parallel to the direction of energy transport. A reflection of sound is an echo. In a concert hall, there are discs on the ceiling to reflect sound, so people can hear everything better. Spongy walls absorb sound instead of reflect sounds, so our classroom is assigned to absorb sound by the ceiling so the other classrooms won't get distracted and hear us. A longitudinal wave can be created in a slinky, like we did in our lab a few weeks ago. In this case, each individual coil of the medium is set into vibrational motion in directions parallel to the direction that the energy is transported. The speed of sound depends on the properties of the medium through which it travels. In air, the speed increases as the temperature increases. Sound does not always travel in straight line paths. Temperatures and winds affect sound. Sound travels a bit faster in warm air near the ground than cold air above the ground. In cold air, air molecules are more dense, so it's harder for the sound waves to travel through. While in warm air, there is more space to travel through, which makes it go faster. The speed of the wave is controlled by the medium. Sound is affected by that. As the air goes away, which means no medium, the sound goes away. The intensity of sound is the sound passing perpendicularly through a unit area. For a sound that spreads rationally, such as from a firework explosion in midair, the sound intensity is inversely proportional to the square of the distance from the source. In fluids and solids, the speed of sound is proportional to the modulus of elasticity and inversely proportional to the density. The intensity level is measured in decibels. 0 decibels is the faintest sound the human ear can detect. The Doppler effect is a change in the frequency of a wave due to the motion of the source and/or the listener. We've all experienced the Doppler effect. When a train races past you while sounding its whistle, and the train is approaching, you perceive the whistle as emitting sound of one frequency, and as it moves away, the perceived frequency of the whistle drops to a lower pitch. Since the speed of a wave is defined as the distance that a point on a wave, like a compression or a rarefaction, travels per unit of time, it is often expressed in units of meters per second. In equation form, it is speed equals distance divided by time. In other words, the frequency of the pulses in front of you is higher than normal, and the frequency of the pulses behind you is lower than normal. The Doppler effect doesn't always apply to sound. It works with all types of waves, including light. Each pulse in front of you would be a step closer than if you were standing still, and each pulse behind you would be a step further apart. One way to visualize the Doppler effect is to think of sound waves as pulses emitted at regular intervals. The faster a sound wave travels, the more distance it will cover in the same period of time. If a sound wave were observed to travel a distance of 700 meters in 2 seconds, then the speed of the wave would be 350 meters per second. A slower wave would cover less distance. So, for example, if the distance was 660 meters in the same period of 2 seconds, and thus have a speed of 330 meters per second, faster waves cover more distance in the same period of time. He learned that the sound waves would have a higher frequency if the source was moving toward the observer, and a lower frequency if the source was moving away from the observer. This effect is named after the Australian physicist who first analyzed it, Christian Doppler. Doppler's research concerned mainly of light from stars, but his principles applied to sound also. Human perception of sound frequency. When a sound wave composed of alternating high and low pressure regions reaches a human ear, the wave vibrates the eardrum, a thin membrane in the outer ear. The vibrations are then carried through a series of structures to generate signals that are transmitted by the auditory nerve to the brain, which interprets them as sound. Frequency or frequencies at which an object tends to vibrate with when hit, struck, plucked, strummed, or somehow disturbed is known as the natural frequency of the object. If the amplitudes of the vibration are large enough, and if natural frequency is within the human frequency range, then the vibrating object will produce sound waves that are audible. All objects have a natural frequency or set of frequencies at which they vibrate. The quality of the sound produced by a natural object is dependent upon the natural frequency of the sound waves produced by the objects.